Okay, welcome. Thanks everyone for joining. My name is Claudio Fahey. I work with on the Dell team. And today I'm going to talk about how to do video processing in Pravega with GStreamer. I'll give an introduction to GStreamer in case you don't know what it is. I will tell you about the Pravega functionality that we have with GStreamer, including a Pravega sync, a Pravega source, how to record video from a network camera into Pravega. And then I will talk about NVIDIA DeepStream SDK for object detection. So that's a GPU accelerated object detection. And the DeepStream SDK can be used for a wide variety of deep learning and AI tasks. And I'll talk about them at a high level. And then I'll show a quick demo of everything. And everything I'm going to talk about is of course part of the Pravega open source license. Okay, so GStreamer introduction. So what is GStreamer? So GStreamer calls itself a pipeline-based multimedia framework that links together a wide variety of media processing elements. So what does that really mean though? So I'll give you some examples. So the simplest example is GStreamer comes with a command line tool called GStreamer launch. And then you can give it a description of a pipeline, just write it out in text on the command line. And you can include various elements. So there's an element called V4L2 source. That's a video for Linux to source. So this is an element that runs on Linux, and it'll capture video from your camera. And then there's another element here called X264 encoder that'll compress the video, the raw video coming from your camera, into H264, also known as MPEG or MPEG-4. It's got many names, but it's basically compressed video. This exclamation mark you see them will link these two elements. So the output of your camera from video for Linux to source goes to the X264 encoder. And the output of the video encoder goes to another element called file sync, which writes to a file. And in this case, the name of the file is called myvideo.h264. So that's the name of the file, and it'll save that to my disk. And I can run that, and it just captures the video. The camera turns on, and it writes the file, and it'll run until I hit Control-C. So that's a very simple command line tool with GST launch. And I'll show you a few more advanced ones as well as ones that include Pravega. Okay, so GStreamer is a lot more than just this command line tool, although people usually start off with using it that way. I can build complete applications that use GStreamer as a library. I can write those applications using almost any language, Python, C, C++, Rust, Java, and more. You can build a video player, video server, DVR, a video management server, almost any application that's going to show video or audio or record it. It can be created with GStreamer. There are also 2,000 plugins available, or nearly 2,000 plugins available. So each of these elements here comes from a plugin. And on the GStreamer website, you can look and you'll see 2,000 plugins available to do various tasks, from connecting to various devices or doing some sort of video or audio processing. It has pretty much everything built in already, and it's pretty easy to make your own. You can write your own plugins in Python or C or Rust. You can't use Java for creating plugins, but you can use many other languages. If you guys have any questions, feel free to put them in the chat, and then I will look at them periodically. And I'll also ask for questions at the end of the presentation. Okay, so what can I do with GStreamer? Here's another example. I can play media from a video server, from a web server, a plain web server that serves files, and show it on the screen. So in this command, I use GST launch again. Playbin is the name of the element. That's a very powerful element. It will download the element, the file from a website, and then just figure out what it needs to play it. It figures out what kind of video compression, audio compression it uses. and it'll just play it on the screen. So here I can see I'm playing that, although it's on the slide, it's just a static image, but this will, if you ran this on your computer, it will play this short video. Okay, so what else can I do with it? I can continuously capture from a network camera and write to a fragmented MP4 file. So that's just a little bit more complicated. So a network camera is something that is connected to a network. Either it's a wired camera through Ethernet, or it could be a wireless network. And I connect to it using IP. And the IP-based protocol is that is common for network cameras is called RTSP, real-time streaming protocol. And that's based on several other protocols if you really want to get deep into it. But all you need to know for RTSP is the IP address. Sometimes you need to know the path, and sometimes you'll need to know your username and password for your camera. So you'll type that here in the RTSP source location. Okay, another exclamation mark, because we're going to link it to the next element. Here I'm going to what's called a DPay. I'm going to de-payload the H.264 stream from this. So RTSP can have audio and video, and it can have different types of compression algorithms in it. And this will tell it to pull out specifically the H.264 payload. And then I can send it to an H.264 parser, which does not decompress it. It simply it figures out where the H.264 frames start and end and some attributes. And then that is sent to an MP4 MUX with a fragment duration. So this is actually what creates the MP4 MP4 fragmented file. Although it's not written to a file yet, it just creates the buffers that will be written to the file. So it puts it into that container format. And with fragment duration of 100 means it's going to write a fragment of 100 milliseconds, and then end the fragment, and then it'll write the next fragment of 100 milliseconds. And then all this will get written to this file. And I can do something like play the MP4 file in something like VLC, and it'll detect it as a streaming file. And every 100 milliseconds, it will get a new fragment of that file, and then it'll play it. Okay, so that's there's a lot going under the hood in that, but it's fairly simple to write. I mean, it takes just 2 lines to write that. I can do something more complicated, such as transcode a media file. So transcode means I have a file in one format. I want to write a new file in a completely different format, but I have the same content. And in this case, I'm going to take it from this website again. I need to put things into a queue so I can run things concurrently on different threads. I'm going to use, there's an audio encoder and a video encoder. So the video encoder is called the Theora encoder. And then that's going into an OGG MUX, which is similar to MP4 MUX, but it's a different format. But the MUX will take the audio and the video, splice them together so that they can be written to a single file. So when you play back that single file, you have audio and video. And then the output of the MUX goes to the file sync. And then also in the same pipeline, we have the audio conversion part of that. So it looks, this is this pipeline has more than one direction. Well, it has more than one flow in it, which I'll show you graphically later. So it looks a little bit complicated written out in one line. So it'll make more sense in the next slide. Okay, so here's actually how the elements of the transcode are represented in GStreamer. So GStreamer takes that command line that I wrote, and it actually builds out all of these elements. I'm not going to go through each one, but I do want to highlight that it starts off here with just one element. So this is reading from the file. And then here it starts splitting up into audio and video. So it can process the audio and video separately. It'll decode the audio and then resample the audio, encode the audio, and then it gets merged together into a single file in the muxer. And the same thing happens with the video channel. It gets split, and then decodes, encodes, and then merges. And this is a little bit zoomed in. You can see the Theora encoder and the FLAC encoder, which is for audio. So the pipelines can be very sophisticated if you want, and it wasn't all that hard to actually build that out. And GStreamer takes care of making sure that all the buffers are compatible. So the buffers are what are basically the data that flows from one element to another, and it has strong typing in there, so you can see that whenever data flows from one element to another, it knows exactly what it is. So this is raw audio. Here's the rate channels and even the type of format. And every single line between elements has a particular data type. So those data types help you build compatible pipelines. Okay, so what about Pravega with GStreamer? So I haven't talked about Pravega yet. So let's talk about that. So there are 2 plugins available for GStreamer that work with Pravega. So one of them is called Pravega Sync. It's a lot like the file sync, although a lot more powerful. So the Pravega Sync writes video or audio or both to a Pravega byte stream. It also writes a time index to an auxiliary byte stream. That time index is used for seeking quickly to a particular place in the video. So I can say I want to go to exactly 30 days ago and start playing from there. And it can seek to that very fast. It's also used for building a playlist if I want to use HTTP live streaming, which is a browser-based video technology. So basically, the index can give you a very a quick view into the entire stream that was written out, because at every keyframe it writes an index record, and I'll show you the details of that a little bit later. The Pravega Sync is they can write any kind of buffer in GStreamer. It could be any format. What works well with some of our use cases is using either the MP4 container format, and specifically it's a fragmented MP4 container format, or an MPEG transport stream. They both work really well. Right now we're leaning toward MP4. It seems to work well for all of our use cases. The Pravega Sync will also write timestamps as 64-bit nanoseconds since 1970. And to avoid dealing with leap seconds, it stores everything using atomic time, which is same as UTC, but it doesn't go backwards when leap seconds occur. Okay, the Pravega source is basically the inverse of Pravega Sync. So it'll read from a Pravega stream and then output that to the rest of the GStreamer pipeline. Together, the Pravega Sync and the Pravega source have very low end-to-end tail read latency. So if a Pravega Sync writes a video frame, the Pravega source will read it usually within 20 milliseconds, which is going to be less than a frame. So it's going to be less than a frame away. Because it's a true stream in Pravega, there's really no difference in the API whether it's a historical read or a live read. It's just a read from Pravega from a particular offset. So writing an application that reads either historical or live is exactly the same, actually. You don't need to distinguish between them. The Pravega source has efficient seeks because it has a time index. Another thing that we can do with Pravega is truncate streams. So you may be writing a year of video data over time, and you want to then, you're filling up your disks, you need to make some room. So you want to delete the oldest data. So Pravega can handle that very well. You just specify the offset or the timestamp that you want to delete things at, and it'll delete all the video or audio before that time. So it deletes the oldest events, and it can be very precise. It'll delete it at any the keyframe keyframe offset. Okay, the Pravega sync and source are written in the Rust language, and it uses the Pravega Rust client. But you can write your GStreamer applications in any language that GStreamer supports. So you can still write your application in Java or Python or C, and it'll just use the compiled Rust library for the GStreamer Pravega. And all of this is open source Apache license and available at the same GitHub site that has Pravega. Okay, so let me show you a little bit about the Pravega byte stream format. So the Pravega byte stream is a very flexible format. It allows applications to write pretty much any sequence of bytes to a Pravega stream. And there is no framing enforced by the Pravega client or the Pravega server. It's just a sequence of bytes. It's up to the application to make sense of that and write it out in a way that can be read reliably. So the GStreamer plugins have a specific format that they use so that this is reliable. So there's there's two streams, as I mentioned. There's the data stream, which is where the video and audio payload gets written to, and then there's the index stream. So the data stream is on top. And this represents two individual events written. So the first one is this the first four blue boxes. So everything it writes is written. It starts with an event length, and this is the number of bytes that the entire event is gonna contain. And then there's a few flags. For video, we have discontinuity and random access. So this is used by readers and decoders to know when they have to restart their decoding process. And then random access is used to know when there's a keyframe and you can start off a decoding at that particular frame. And then it's expandable to more flags as needed. Here we have the timestamp, which, as I mentioned, is nanoseconds since 1970. It's a 64-bit number, so it won't wrap until about 200 or something years from now. So it's storing this very high precision number is not really a problem. And the nanoseconds precision is what GStreamer uses internally. So that's why this is stored in Pravega. And that's high precision enough for even very high precision audio. A very high bit rate or a high sample rate audio. Okay, and so that's followed by a generic payload. And so this payload could be something like an MPEG transport stream packet, which is 188 bytes, or it could be a multiple of 188 bytes, or it could be an MP4 fragment, which may contain information for a single video frame or several audio samples. And it's for video, this could be a single keyframe or it could be a single delta frame. In fact, you can even make it so it's a keyframe plus multiple delta frames. The MP4 spec is very flexible, so you can pretty much make it. You can write whatever it is you want, whatever frequency you want to write it at, or whatever size you want to write it at. It'll do that. And this will be 0 to 8 megabytes. So if you want to write more than 8 megabytes, perhaps because if you have a keyframe larger than 8 megabytes, the Pravega sync will simply fragment that, and you'll get multiple events. You'll get another event here with its own event length flags timestamp, and the payload, which is the remaining bytes. So you can write more than 8 megabytes. It handles that well. So this whole thing here is an atomic write, which is a primitive that Pravega supports, and it's extremely useful here because it means that either the Pravega sync writes the whole thing or none of it, which means that when I'm reading it, I know that either the whole thing is there or none of it's there, so that there is no possibility of writing an event length without the entire payload following that. if that were possible, then they would lead to unrepairable corruption in the stream. So to prevent that, we have atomic rights, and that allows it to be that allows for no corruption. Yeah, even in scenarios where you have network outages that occur right in the middle of a write. Maybe I'm writing a 7 megabyte buffer and the power goes out halfway into that write. I'll be sure that I don't have half of a event written to Pravega. Okay, so the index stream it basically has 20 bytes per keyframe for video. We have flags. These are the same flags as what you have up there. Then you have a timestamp, which is the same timestamp as what you have in the data stream. And then you have a byte offset, which is a 64-bit integer, which is the number of bytes into the data stream that this event starts at. And then that just repeats every time there's a keyframe. It's about, and it's 20 bytes per frame. And it's, of course, it's ordered, so it allows for very efficient seeking. I can have a year's worth of data that's indexed, and you can just do a binary search to find the right timestamp that you need. Or I can do a scan of the entire index, and I can have a pretty good idea of the timestamps and the bit rate for the entire stream. And I can also do truncation at any point. I can just do a truncation right here at this boundary, or I can do a truncation at that boundary. As long as truncation occurs at an atomic write boundary, you also need to make sure that the truncation at the index stream is consistent with truncation at the data stream. But that works really well. And you can even truncate as you're writing more data, as you're recording more data from cameras to Pravega. Okay, so how do we do recording of video from network cameras into Pravega? So here's an example of recording from two different cameras. So we start off with a network camera, and then we have a GStreamer pipeline. So that's similar to the GStreamer pipelines that I showed you before, where you have the RTSP source right into Pravega. That's all this really is. You have an MP4 mux and a Pravega sync. And then it's writing to the video data stream and the video index stream. And then I have another camera writing to a different video data stream and a video index stream. So every single camera writes to its own stream that's dedicated to that. And this is still efficient because Pravega writes everything to segment containers. So it's not a problem at all to have thousands of video streams on a single Pravega cluster. It also allows for very efficient reading. So there's an application called Pravega Video Player, which will read video from a single stream and then play it on the screen, just as a standard, just as you would expect a video player to do. It's got a seek button, or a seek slider, so I can choose any point in time, and it'll take me to exactly that point and show me the video from that point. Okay, and I'll show you that in a demo in a little bit. Okay, so now I'm going to talk about NVIDIA DeepStream SDK. Okay, so what is the NVIDIA DeepStream SDK? So it's an analytics toolkit for AI-based multi-sensor processing. So and it supports video and image data. So it's built around GStreamer, and it has several GStreamer plugins. One of the plugins is a hardware or GPU accelerated H.264 decoding and encoding and deep learning inference. They have a lot of other GPU accelerated plugins as well, or elements. But the most important ones that we're going to be using are these three. So this requires an NVIDIA GPU, which could be a full PCI card GPU, a server class GPU, or it could be something like a Jetson Nano, which is very tiny box that you can integrate into small robots or small applications. But it does require some sort of NVIDIA GPU. It won't run with just a CPU. Okay, so Pravega integrates with NVIDIA DeepStream with the Pravega protocol adapter. So the Pravega protocol adapter, it's an implementation of the DeepStream message broker. So one of the things you can do with DeepStream is object detection inference. So the output of object detection inference is basically for each image, it's going to be a bounding box saying, here is a bounding box. Here's the X, Y, height, and width. And I believe that there is a car there. And I'm 0.5, I'm confident with a 0.5 probability that there is a car there. It might also do things like read the license plate number and output that with a certain probability. So that information is output using the DeepStream message broker interface. And that can be written to Pravega as JSON, for instance. So you can have a Pravega stream. In this case, this would be a Pravega event stream with that JSON data. I'll show you an example of that on the next slide. If you are using an existing DeepStream application that uses the message broker, you may be using that to write through some other message bus system, but you can just change one line in there and it will use Pravega instead. The Pravega protocol adapter is not used for video or audio data. You use the Pravega sync for that. The Pravega protocol adapter is also written in Rust, and it uses the Rust client. And this is also open source Apache licensed. Okay, so here's what it looks like to do real-time video object detection. So it starts out the same as the previous slide that I showed you, where we have a network camera, a camera recorder GStreamer pipeline, and that writes to Pravega stream. This first one is called camera 1. That's the name of the video stream. There's also an index stream, which I'm not showing just to simplify the diagram. Okay, now currently I'm running another GStreamer pipeline, which I call object detection GStreamer pipeline. It is accelerated with the NVIDIA GPU. So this object detection pipeline, first, it needs to decode the compressed video. That is GPU accelerated, and then it needs to run the deep learning algorithm to identify the objects. The output of that deep learning algorithm looks a lot like this JSON snippet. We have a camera ID to identify the camera. We have the timestamp of which corresponds exactly to the frame when it was captured by the camera. So that timestamp is maintained throughout from camera sensor all the way to object detection. So this is accurate to within hopefully nanoseconds. So this identified a vehicle. If you have the right AI modules, it will detect the type of vehicle, color, the license plate number, and here's the confidence number of it. And here's the bounding box and coordinates of the screen. Okay, and so the JSON output of each of these two pipelines, it can go to the same stream, which means I can then run a streaming analytics job using Flink, for instance, like what Brian just showed you. And now I can analyze the metadata from all my cameras using one Flink job. I can also use Spark. Or you can use any analytics framework that Pravega supports. I can also configure the object detection pipeline to create a new video stream, which is just like the first video stream, but with the bounding boxes and the name of the object burned in, essentially. So it's basically drawing the red rectangles here into the image. And then I can view that again using the Pravega video player, because now it's just a standard stream. And the video player could play the original stream from the camera right here, or I can play this one here with the on-screen display with the rectangles. Okay, so here's a demo. I was going to show you in real time on a real system, but that's not going to work right now. So I'm just showing you a pre-recorded demo. What I'm doing for the demo is I have a camera recording. This was this is a camera on my desk, but it was a network camera, a wireless network camera. On the left window here is directly from the camera using VLC media player, using the RTSP protocol. That was getting recorded to a camera stream that was in the cloud, so in a different state across the country. And then I have a Pravega video player playing from that Pravega stream in the cloud. And this is before object detection. Then I have then I'm running object detection on GPUs in the cloud. That's being written to the on-screen display stream, and then that's being displayed in the Pravega video player here as well. So you will see a few seconds of latency from the left side to the right side. A lot of that latency is caused just by going across the country here. Some of the latency is caused by the GPU, and very, very little latency. I mean, just milliseconds is actually caused by Pravega itself. So I'll play this and you can see what that's like. So it's detecting the car, and you can see on the right side, it sees that there's a car. And as I move the car, you'll see that the bounding box also moves as well. And then the bounding box jumps around a little bit, like on the free frames, there actually is no bounding box, which means that the orientation of it, it just prevents this very basic object detection from detecting that. So that's something that is just a limitation of this particular trained model. This is the pre-trained model that NVIDIA provides as part of their DeepStream SDK, and it's a good starting point. But in a real application, you're going to want to retrain your model with your own data, just to get the best performance and reliability out of it. And of course, and also this model is only trained by is only trained to detect cars, people, signs, and bicycles. And in the real world, you'll want to test with more than that. Okay, so that's all I have to show for now. Hold on, well, that's all for the slides. If you guys have questions, go and ask them now. I also have I can show you a few things on the screen here for what you guys can do to start this up and run it on your own environment. But if you have questions, go ahead and start asking now, or just put it into the chat. Okay, so the first thing I'm going to show you here is, so I already downloaded the open source code from the repo. That's the GStreamer, the Pravega repo. So the first thing I'll do is start my own instance of Docker. So, sorry, not Docker, Pravega in Docker. This is different from the standalone installation because all the data is stored on disk, not in memory. The normal standalone Pravega stores everything in memory, which is great for simple testing, but for video, you'll run it in memory very quickly. So I use this script called up, and this will run everything in Docker. So I'll show you how that starts up. So right now it's stopping the previous installation. And this is a non-HA version. So it's only one instance of every type of container I need. Okay, so it's starting up. I don't need to look at all the logs. It is good. Okay, so I'm gonna go to the next window. And now I'm gonna run RTSP camera to Pravega Python. Okay, so this will connect to my RTSP camera, and then record, basically record it to Pravega stream. Okay, so now it's running, and the only thing it shows on the screen is that it's every 2 seconds approximately, it's writing a new index record, because that's when it gets a keyframe from the camera. Okay, so now we're writing it to Pravega. Now I'm going to view the screen. I'm going to view the video on the screen using the Pravega video player. Oh, and one thing to mention is I ran the command and it ran very fast. The first time you do it, it might actually take you 20 minutes because it has to compile everything on your system. So if you didn't already compile it, give it about 20 minutes, and hopefully you have plenty of memory and CPU power to make that go faster. But the second time you run it, it'll be very fast, just like as what you saw. So here's the Pravega video player playing back the RTSP stream. Oh, look, someone's there. Okay. So and it starts off at the very beginning of the stream. But I can go to the very end of it, and now it's pretty much live right now. Let me get to the very end. I mean, it should be about maybe 1 second or less behind real time. And I mean, not much happens on this particular camera, but it. Yeah, but if I have 30 days of video, it would all be available here on this slider. And every single frame tells me the exact UTC time that the frame was captured. So that's going to be useful for very precise object detection. Okay, and then another thing I can do is the Pravega video server. So this here is a Linux native player. It can also be built for Windows and Mac without many changes. But it is native, so it won't run in a browser. A browser-based video player is served by Pravega video server, and here is what that looks like. So I just go to the URL served by that server, and I basically have the same thing here. But here I have the seek bar just like before, and I can play things. And this works in any browser, and it just needs port 80 or whatever your HTTP port. It just needs to pass through. The only drawback with this is that this uses HTTP live streaming, which is an Apple standard that works really well. But the latency is pretty high. So you might be about 5 seconds or 10 seconds behind live video. So it's not real good for watching live video. But if you want to watch historical video or anything older than 5 seconds, it works great for that. And it works across pretty much any browser, including mobile. So I think that's it for the demo. Are there any questions or anything else someone would like to see?
Yeah, I guess I had a question similar to maybe the DeepStream message broker that you wrote an adapter for. Like, there are some GStreamer elements that produce GStreamer messages on the bus as a part of their, like, for example, the level element. I can basically make VU meters, and it'll produce like a G object data structure per interval. Would I be able to tie in with the Pravega sync and record those like decibel levels onto an alternative stream? Or
I believe so. The GStreamer sync will write any buffer. So any buffer that it has, it will write it to Pravega. It'll put it into the payload section that I showed you.
Mm-hmm.
Let's see. Let's see. Yeah. So, and the information that it records for every single buffer is just the timestamp and the number of bytes. if there's other metadata that your use case uses, that it may not be captured. Yeah, so like there is information in other information available in the buffer, such as duration. There's also the DTS, the decode timestamp. That information is not stored in Pravega because it's typically not it's not used by the use cases that what we typically find. But if you need something basic like the PTS, which is the presentation timestamp, that's the main timestamp, then you should be able to store it and then decode it with the Pravega source.
Cool.
And it'll also index it for you in case you want to seek to a particular position. Okay, well, I think that's it then.
Yeah, that was great. I'm sure GStreamer is new to a lot of people, but that was really cool.
Yeah, thank you.